Okay. Now that it's recording, the filter turns on. So gotta watch out what I say. Actually, it's unknown. We did a simplified example where we calculated the confidence interval on the mean if we knew the variance. Now, I already mentioned that's really highly simplified. Because in reality, if we don't know the mean, then we don't know the variance. Right? We're not gonna know the variance of our population, at least offhand. And if we do know the variance, then we most likely know it. We know it because we know the mean. So now let's see what happens when we don't know the variance. Okay? So what I'd like to work on now is what happens when we don't know the variance and we still want to find a confidence interval on the mean. Now, we're going to work with large samples first, then we're going to go to smaller samples. And with large samples, and when I say large, I mean a lot of measurements. Think of more than 40, for example, more than 40 observations. Could be more, could be less, but a lot of observations. We mentioned a couple of things, right? We said, if I remember correctly, we said that if you take the sample mean of a bunch of observations, the greater your observations were, the bigger the number of observations was, so the bigger n was, then the more that sample mean tended towards normal distribution. So we're going to take advantage of that. We're going to say that we are selecting from a large sample, n is a very large number, such that the probability distribution of the sample mean is going to look like a normal distribution. Now, it doesn't matter if your population has a normal distribution. What matters is that the sample mean has a normal distribution. So we already defined z as a standard normal random variable that was equal to x bar minus mu divided by sigma over square root of n. We can't really use this here because we don't know the variance. If we don't know the variance, then we don't know the standard deviation. However, you may recall this one thing that we talked about back when we talked about organizing data. When we compared the variance and the sample variance, we saw that the larger number of samples was, then the closer the two were to each other. Now what that means is that if you have a very, very large sample, then you could, in theory, replace your variance with your sample variance. Because even though they're not going to be exactly the same, the difference is going to be so small for large sample sizes, so small that your z value is not going to change that much. So we can approximate our z random variable as the sample mean minus the population mean divided by the sample standard deviation over square root of the number of observations. And of course, the number of observations is going to be very large. From here, we can move forward and repeat the same analysis we did in the last exercise, where we already know that the probability that my random variable z is between negative z of alpha over 2 and z of alpha over 2 is simply 1 minus alpha. Combining these two and rearranging, I get a confidence interval for a large sample with unknown variance, where in place of the unknown variance, we calculate the sample variance. You can see that the interval is virtually identical to the one we calculated earlier, except that in place of the variance, or in this case, in place of the standard deviation, we use the sample standard deviation. A 95% confidence interval would then be the one corresponding to the z-score of 0.025. And we already know what that z-score is, right? It was 1.96. So this is how we would approximate, or how we would get a confidence interval for a sample if we don't know the variance, assuming that the sample is a very, very large sample. Let's start an in-class problem today. I posted a spreadsheet on your content section on D2L. If you go to content on D2L, and you go to the module 12 folder, there's a spreadsheet called module 12 data. You don't have to use it if you don't want to, but I recommend you do because it's going to be easier than having to write down all of the values yourself. I'm going to share the data with you as well here on the screen. And let's say that we have 53 samples. These 53 samples correspond to measurements of mercury contamination in largemouth bass. Is the fish bass? Is it pronounced bass? B-A-S-S?
I think it is.
Because I know the instrument is pronounced bass. Perhaps the fish is pronounced differently. Maybe you can help me with that. So we have these 53 measurements of mercury contamination. And for your reference, I've also plotted these measurements, or the book has also plotted these measurements in a histogram. Now looking at this histogram, do these measurements follow a normal distribution? Oh, in the chat, there's a question, where can we find the data? You will find them in the content section on D2L under the module 12 folder. This is module 12, so you can find it under the module 12 folder. It's a spreadsheet. Christian says, not really, in the chat. And that's right. It doesn't really look like a normal distribution. You can see that you don't see the symmetry here. You don't really see the bell shape. You see that it's kind of oscillates a little bit. It's not a normal distribution. However, we have a lot of samples. And because we have a lot of samples, even though the samples, the individual values themselves won't follow a normal distribution, we can assume that the distribution of the sample means is going to be normal. The reason I want to show you the histogram is so that you can see that this will work even for samples that don't follow a normal distribution. So I want to find a 95% confidence interval on the mean of this mercury contamination. For your submittal of your in-class problem, we're going to have two problems today. So for your submittal of both problems, my recommendation is that you open the Excel spreadsheet, do your work in the Excel spreadsheet, and then just upload that Excel spreadsheet. Okay? That way it's easier. You don't have to upload anything else. But make sure that your Excel spreadsheet has the equations attached to them, because for this in-class problem, I will look at your equations, make sure that you're actually solving the problem and not just typing the answers, as you're actually putting the effort to solve the problems. I'd like to find a 95% confidence interval on the mean of the mercury contamination. Right? In this case, we have 53 measurements. So if I would like, I can figure out, and let me just get rid of this. I can figure out what my n value is. We have 53 observations, therefore n is going to be 53. Okay? You don't have to count them yourselves, I'm telling you this, right? It is 53. We have 53 values there. If we want to find a 95% confidence interval, you can go back to your equations, which are in your notes, and you can see that for those equations, we will need the sample mean, x bar. So the first thing I would recommend that you do is to find that sample mean, or x bar. In this case, the sample mean, Ramtin already explained this to us before, is taken by adding up all of the values in our sample and then dividing it by the number of observations. This gives me a sample mean of about, and I'm going to round it to 4 significant figures, of about 0.5250. Okay? That is the sample mean. So we found the sample mean. We looked at our equation for a 95% confidence interval when we don't know the standard deviation or the variance. And we see that that equation requires us not just to find the sample mean, but we need to find the z-score for 0.025. What was that z-score again? We get it from the table? From the z-score table?
1.96.
1.96. Good. Good. Looking at that equation, Michael, what else do we need?
Don't we need the variance or sample variance?
The sample variance. In this case, it's easier if we just get the sample standard deviation, which is the sample variance, right?
Yeah.
And the square root. Yep, correct. So we do need the sample variance. So you can find the sample variance. I don't really have to explain the procedure because we've already done sample variance examples before. So I'll just try to do it relatively quickly. Let's see, for my sample variance, take each measurement and subtract from it the sample mean, right? I think that's how we did it. And then I have to square these values. That's what I'm going to do now. My sample variance, or S squared, is going to be the sum of all these values divided by n over 1. Or n minus 1, my apologies. So I get a sample variance of 0.1215. My sample standard deviation is going to be the square root of that value. If I round it to 4 significant figures, I get 0.3486 for my sample standard deviation. Notice that we've already found everything we need for this problem. We looked at our observations, we found the number, we counted the number of observations, found the sample mean, found our required z-score, found our sample variance, and used it to calculate our sample standard deviation.
Sorry, I was doing the part 1. How did you do the sample variation?
I think that's something that we've already covered in previous weeks. So you can look at your equations from your notes on organizing data, and then just use the same equations. What I did in this problem, just to make my life easier, is because the sample variance corresponds to your observation minus the mean squared, then I just repeated this table where every value is the value minus the mean squared. And then I added them up and divided by n minus 1 to get my sample variance. I think that's about as much help as I'm willing to give, just because this is not really new material. This stuff we've already done before. So we've got all these values, and I'm going to write them down in my sheet of paper so that we can continue to use them. And in the chat, we got a question about the table. So I guess the answer is just the same answer I gave around table. Right? So I've written down my values, 53 for my number of observations, 0.5250 for the sample mean, 1.96 for the z-score, 0.1215 for the sample variance, and 0.3486 for the sample standard deviation. Writing those values in my 95% confidence interval equation, I give them my 95% confidence interval has my mean in between the following values. Sample mean minus z-score times sample standard deviation over square root of number of observations and if I do a little bit of math and solve these values, I will get that my mean, there's a 95% probability that my mean is in between 0.4311 and 0.6189. That is how we would find the mean, or let me rephrase that. That is how we find an interval for the mean if we don't know the variance or standard deviation of a population. We can use this equation only because we have a large sample. 53 is considered a large sample. More than 40 is considered a large sample. So we can use this expression. If our sample were smaller, then unfortunately we would not be able to use this expression. I'm going to give you a few minutes to wrap up your calculations, but you don't have to upload it yet because we're going to do another problem, and I would like for you to just upload one file for both problems.
Oh, there it is. Instead of dividing by the box of n, like I divided by this, which is n is equal to, I just plugged in 52 instead of trying to do the box one. So, and it seems to work.
Once you have this first problem completed, let me know when I can move forward. Go ahead, Simon. I see you have a question.
I'm behind because my computer is messing up. What did you do with the next table? Did you arrange from the smallest to the largest so that you can be able to find the, what do you call it?
So Samuel, the speakers in this room are actually really low.
Yeah.
I
saw you had
the speakers are really low. Would you mind typing your answer, your question in the chat so I can answer? I can hear you, but I cannot understand because the speakers are not very good here.
Just the values a little close.
Yeah, I only have 3.
Okay, so it looks like Renee is already answering the question. That's good. Thank you, Renee. Remember, you don't have to do exactly what I did. If you have another way of calculating the sample variance, then use it, right? Because you can use it, you can calculate with the equations that we covered in the previous weeks. Sam, do you have another question? And if you do, just my apologies, but the speakers here are not good. So if possible, you can type the question in the chat, and then I can answer from there. Oh, the question was that I have two tables to calculate the sample variance. Well, I mean, I just created a table just to help my calculations because sample variance, you already know from your equation, from your notes, sample variance is equal to the sum of all of your elements minus the mean, square that, add them up, and then divide by n minus 1. I just found it easier for myself to just do all these individual calculations in a separate table. Right? You can calculate them however you prefer. You don't have to do it exactly the way I did it. Okay? And of course, my focus is on the confidence interval. So yeah, I don't want to spend too much time covering things that we've already explained in previous weeks. And if you need a little help, I'll write down the sample variance equation here.
So would you want us to just, if we're all putting it on the Excel, you just want us to calculate the lower and upper limit for the 95%? See that?
Hmm?
Okay.
Yeah.
Gotcha.
Online students, what Michael asked was, if we're going to submit an Excel spreadsheet, I want you to just calculate the lower and upper limits. That would be good, yeah. I think that would be good. You can give me the lower limit
This one.
and then the upper limit for your confidence interval. Make sure you highlight your answers somehow so that I can figure out what they are. For the lower limit, I have my sample mean minus, let's see, I have my z-score times sample standard deviation divided by the square root of the number of observations. I get about 0.4311. Then for my upper limit, I have my sample mean plus my z-score times my sample standard deviation divided by the square root of the number of observations, which gives me about 0.6189. Oops. There we go. So yeah, if you can show me these two and the calculations that you did to get to these, then that should be good enough. And make sure you highlight them somehow so that they stand out from the rest of your work.
Is it okay if you just type in the calculations into the box?
Yeah. Let's move forward. With this example, what we did was to show, right, show how to get a range, right, a confidence interval if our sample is very large. Because if our sample is very large, we can assume that the variance and the sample variance are very close to each other, which means that we can replace this variance with my sample variance. However, sometimes we don't have large samples. And of course, when that happens, we need to find other methods to find our confidence interval. So let's now take the next few minutes to talk about how to find a confidence interval on the mean if the variance is unknown. And this would be for any type of sample, large samples and also smaller samples. If my sample size is small, let's say, just to give it a number, let's say less than 40, my sample size is small, then we cannot use the methods that we've used before to solve it, to solve for a confidence interval. If my sample size were large, we could just replace my variance or standard deviation with the sample standard deviation because the difference between them would be very small. If the difference between them is small, then the effect that changing between them has on the distribution is also small. If we want to do this, if we want to replace the variance with the sample variance, or in this case, the standard deviation with the sample standard deviation, and our sample size is small, then we will need to account how different, right? How different the sample variance and the variance is. Okay? So here is where the student's t-distribution comes into play. Now, earlier today, I talked about the student's t-distribution. I mentioned that we're going to figure out what we would use this distribution for. Okay? So from the student's t-distribution, we know that a random variable t, which is equal to the sample mean minus the population mean divided by the sample standard deviation over the square root of the number of observations, we know that this random variable will follow a student's t-distribution and will have n minus 1 degrees of freedom. So we'll say k, which is the degrees of freedom, will be n minus 1. We know that much, we already covered this. Now here's the thing. Looking at the student's t-distribution tables, then we could say that the probability, just like what we did with the standard normal, we could say the probability that my variable t falls in between the t value for alpha over 2 with n minus 1 degrees of freedom and t of alpha over 2 with n minus 1 degrees of freedom is simply 1 over alpha. So what we're doing here is we're repeating the same procedure we used for the normal distribution, where we know, because the t-distribution is also symmetric, we know that the probability that my t variable, my random variable t, falls in between negative t of alpha over 2 and positive t of alpha over 2, we know that probability is simply 1 over alpha. Remember, I mentioned that t-distribution will look like the normal distribution, except that it's flatter. But it's still symmetric, like the normal distribution. So combining these two and rearranging, I get that there's a 1 minus alpha probability, right, that my sample mean lies in between the following values. And I'm getting these values by replacing this t with this expression and then solving for the sample mean. It'll be in between x bar minus t of alpha over 2 with n minus 1 degrees of freedom times the sample standard deviation over the square root of the number of observations. And on the other side, I have the sample mean plus t of alpha over 2 with n minus 1 degrees of freedom times the sample standard deviation over the square root of the number of observations. Of course, for a 95% confidence interval, that alpha will be 0.05, and therefore this will be the t-value of 0.025 for n minus 1 degrees of freedom. So, because we want to focus on 95% confidence intervals, in this case, the 95% confidence interval will be the following. So this would be the confidence interval for a sample if we don't know the variance, and also if the sample size is not that large. Because it's not that large, we need to account for the difference between the sample variance and the variance. Notice that this is actually just a generalized form of the previous method, because we already said that if k tends towards infinity for the student's t-distribution, that means that the t-distribution will look like a normal distribution. And in the previous method, all we did was assume a normal distribution. So what we're learning now is a more generalized form of what we did earlier. Let's work on our second in-class problem. Again, you only have one submission, don't worry, but both problems in the same submission. So let's work on the second in-class problem for today. Make sure you write down this equation. That way you can use it. In your solving of the in-class problem.
So wait, real quick. So for the, we'd have to look at, we're going to look at use the T table that you were talking about?
Yeah.
Okay. That's just going to be in
Appendix. Yep. And in this book, it should be appendix, I think, table 5. But let me double check that. It is? Okay, thank you, Sean. Yep, T table is appendix table 5. Notice that this is actually the same, or not the same, this is very similar to the equation that we derived earlier, except that in the earlier equation we looked at the z-score tables. In this equation we're looking at the t tables. That would be the difference between the two. All right, it's appendix table 5. Thank you, Sean, again, for the help here with the pages.
Table 5.
So for this next example, let's look at alloy adhesion and alloy adhesion problem. This table shows 22 samples of some alloy specimen. I showed a box plot so that you can see that the data is more or less, it is normally distributed. I mean, you can see that the box plot is symmetric, right? It's symmetric about the mean, and the whisker is also symmetric. So this kind of gives us a clue or implies that the data could be normally distributed. Regardless of whether it is or isn't normally distributed, we can still try to solve it. I would like to find a 95% confidence interval on the mean here. So what do we need? Well, first, I would like to know the sample size, or n. This is actually given. You don't have to count it yourself. I am telling you, based on the problem statement, that there are 22 samples. 22 is less than 40. We're going to say that this is a small sample size, not a large sample size. Because it's not a large sample size, we cannot assume, right? We cannot assume that the standard deviation and the sample standard deviation are similar. So we'll have to turn to our method of using the t-distribution. The next thing I'd like to find is, or are, the degrees of freedom, k, or in this case, n-1. If there are 22 samples, how many degrees of freedoms do we have?
21.
21, correct. Good. Now, let's find for this data, for these data, let's find the sample mean and the sample standard deviation. You may recall that sample mean is found by adding all of these values and dividing by the number of observations. Let me know when you have the sample mean so we can move forward. Again, you don't have to write down all the values in this table. You have it on the Excel spreadsheet in the Module 12 folder. You have the mean?
Yeah, I got it.
Or where do you want to go?
What's that?
You have the mean?
Yeah, I got it.
All right. So let's move forward. For this case, we want to find the t-value corresponding, right, to an alpha or alpha over 2 of 0.025 and to 21 degrees of freedom. We want to find the t-value for 0.25 with 21 degrees of freedom. You can go to your appendix, table 5, and find the corresponding t-value for 0.025 and 21. Remember, the t-value table is a two-dimensional table, which means that you're going to have to find 0.025 and find 21 and figure out what is the value that corresponds to both of those. In the chat, we have 2.08, and that is correct. Let's write it down.
It's on the mouse?
Good. Thank you, Christian, and thank you, Carlos. Now comes the fun part. We gotta find our sample variance and our sample standard deviation. For my sample variance, remember the equation? That's the sum of all my elements minus the mean squared and divided by n over 1, n minus 1. So once again, I'll just perform that sum up here. For my sample variance, I get about 12.63. My sample standard deviation is going to be the square root of that number, which is roughly 3.55. So now it looks like I have everything I need to calculate my confidence interval. Let me know when you have the sample variance and the sample standard deviation so we can move forward.
Oh, I was looking at cheese squared. Yeah, I'm good.
Right, so I've written down the information that we have from our spreadsheet, and we can use this information now to come up with our 95% confidence interval. You can see that that confidence interval will be equal to the sample mean of 13.71 minus my t-value, which would be 2.08, times my sample standard deviation, which is 3.55, divided by the square root of the number of observations, which are 22. On the upper side, we will have our sample mean plus my t-value times my sample standard deviation divided by the square root of number of observations. A bit of math, I get that a 95% confidence interval states that the mean will be between 12.14 and 15.28. I'm going to go back to this sheet to actually show you, or to actually type in the calculations. And that constitutes your in-class problem for today. Put your results together in the spreadsheet. You have until 5 to submit it, so if you don't have it ready just yet, then don't worry, we'll have some extra minutes at the end of class. You can refine your spreadsheet before you upload it. So you don't have to upload it immediately, you can upload it. As long as it's before 5, we should be okay.
Which one is this? Is this number 4 or 5?
I think it's 3.
Oh, correct.
You go to assignments, look at the assignment that has today's deadline at 5 p.m.
Gotcha.
And all assignments are they're in the order of deadline. So you'll find it near the bottom.
Oh, oh.
It's from bottom up, it would be the 4th one. If you go from the bottom up. Right? While you're doing that, we already know how to find confidence interval on the mean if the variance is unknown, which is typical to what you will be actually studying as a statistician or as an engineer who uses or makes use of statistics. I'd like to end today's class with one more topic, and that is the confidence interval on the variance. So far, we've already talked about confidence intervals on the mean. In other words, we've tried to find out confidence intervals for my mean, my population mean. But we haven't really looked at confidence intervals on the variance. So I'd like to talk about a confidence interval on the variance. And for this particular case, let's simplify it to assume that we're dealing with a normal distribution. Unfortunately, this class is not eternal, so we can't look at every single possible example of every single confidence interval on every single probability distribution. But I think the tools that you are being given right now are enough to study most of the physical phenomena that you'll be looking at in your careers as a civil engineer. Things like traffic behavior, things like resistance of civil engineering materials, things like atmospheric and weather conditions. So the civil engineer, looking at normal distributions will be pretty much what you will be seeing throughout your career. So I think what we're learning today is helpful career-wise. Okay? We have a population, and we don't know the variance. We already have a method for calculating the mean if we don't know the variance. However, we would like to come up with a method to calculate the variance, right? We can calculate the mean, but that doesn't really tell us anything about the dispersion of the results. We would like to find out a method to calculate the variance. Let's remember that chi-square random variable, which was defined as the number of degrees of freedom times the sample variance divided by the variance, had a chi-squared probability distribution with n-1 degrees of freedom. Let's repeat the same analysis that we did last time and apply it to the chi-square distribution. We can say that the probability that my random variable, chi-squared, lies in between a chi-squared value of 1 minus alpha over 2 with n minus 1 degrees of freedom and a chi-squared value of alpha over 2 with n minus 1 degrees of freedom. That probability will be 1 minus alpha. Now we gotta be careful here, because here, remember the chi-square distribution, chi-key, chi-key, the chi-square distribution is not symmetric. Because this distribution is not symmetric, then we cannot assume that these values are going to be, or we cannot have these values correspond to the same alpha value. That's why we have 1 minus alpha over 2, and that's why we have alpha over 2 on the other side. So let's keep that in mind, okay? The chi-square distribution is not symmetric, so our lower and upper intervals are going to be different, okay? Or the length of those intervals is going to be different. All right, so let's see what we have. If I have this definition of my chi-square random variable, I plug it into here, and then I solve for my variance, sigma squared, I get that a 1 minus alpha confidence interval for sigma squared is the following. And here, all we're doing is solving algebraically. This is my confidence interval for my variance. Remember, no longer the mean, now we're dealing with variance. We can also say that the upper and the lower confidence bounds are the following. Let's start with the lower confidence bound. I can say that my variance is at least greater than or equal to the degrees of freedom times the sample variance divided by the chi-squared value of alpha for n minus 1 degrees of freedom. Or we can also say that my variance is at least, right, so below, yeah, in this case it will be at least. And the previous will be at most. In this case, at least the degrees of freedom, sample variance, and then my chi-squared value of 1 minus alpha for n minus 1 degrees of freedom. So these are my equations for my confidence interval for the variance, where this gives me the confidence interval in the upper and lower bounds. This gives me a lower confidence bound, and this gives me an upper confidence bound. Yep.
I was wondering why the 1 minus alpha over 2 switch sides there.
Because when we solve, remember when you have an inequality, right? And you have, you have, what do you call it? You want to take the reciprocal of a number, the direction of the inequality changes.
Okay.
Here, sigma squared is in the denominator. So you have to take the reciprocal to solve it. So, such that the direction of the signs changes.
Gotcha.
Yep. So these are our equations. Before we wrap up our class today, let's work on a quick example. This will not be part of your in-class problem, just an example we are working on here. So let's suppose, and this is an interesting example because it is the most practical one of all the ones we've done today. Let's suppose that you are inspecting a detergent facility. You have a detergent facility, and then your detergent bottles are all filled up automatically. So with a machine. Oops. Okay, so you have a little conveyor belt, and some machine fills up your detergent bottles. Okay. Of course, even though we can set a specific volume, different situations and the environment and the machinery are going to cause it, right, to have variation in the amount of volume of detergent that is added to each of the bottles. Okay? So you, as the process engineer or industrial engineer, you decide to select a random sample of 20 bottles and then measure the volume of detergent in each of those bottles. So you select a random sample of 20 bottles and you measure the volume of detergent in each of those bottles. In the interest of time, let's say that you measure the volume and then you calculated the sample mean and you calculate the sample variance. Your sample variance turned out to be 0.0153 squared ounces. Now, I have a question. Why is this important? Think of it this way. What happens, right, if the machine is overcompensating for the volume? If the variance gives, if variation shows that at some point there's a chance that the machine will actually add more volume of detergent than what it can actually contain. What happens? Yeah, you lose detergent. Good. On the other hand, if the machine adds less volume of detergent than the bottle can contain, then it's also not a good thing, right? You typically sell by the ounce, right? So your bottle should have the correct amount. So it's up to you to decide how much variation is acceptable. Now, in your random sample of 20 bottles, you have a variance, remember that's the square of the dispersion, of 0.0153 squared ounces. But these are only 20 bottles. You produce hundreds and hundreds and hundreds every day, if not thousands. So you need to find a way to use these 20 bottles, or the information on these 20 bottles, to figure out or estimate the sample variance, or the variance, not sample, the population variance on all of your bottles. But you don't have time to measure all of them, okay? Here's the thing. Because in this case, what we're looking for is variance, and the larger variance is what's going to affect us, then we don't really need to find both upper and lower bounds for my variance, right? Instead, we are going to want to find the upper confidence bound. We want to know how, we want to know how big my variance can be. So the upper bound tells me that the variance is going to be less than or equal to some value, which means that the value that we get for this upper bound is the smallest possible variance we can get. It's either that or greater. So if that in itself is already causing me trouble, right, then I already know that my system will not work properly. Alternatively, you can also try to find the lower bound of the sample variance and say, well, I just want to know, right? I just want to know, or I just want to get a more nuanced view of my variance. But let's simplify here, and let's just say you want the upper bound, okay? You just want to know that your sample variance has to be less than or equal to some number, so that you know, okay, at least what's the value, like how high your variance can get as upper bound. I write down my equation. My upper bound is actually written right here. I have 20 elements, or 20 samples. So I'll have degrees of freedom, well, 20 minus 1, 19 degrees of freedom. And I have calculated my sample variance to be 0.0153. By the way, there is a typo in the textbook for this example, so just make sure you copy the example from the class, because there's a typo in the book. And of course, now I'm going to have to find my chi-squared value of 1 minus a, or 1 minus alpha, for n minus 1 degrees of freedom. So we go to our chi-squared tables, and because we are looking for a 95% confidence interval, then we will be looking for the chi-squared value of 1 minus alpha, so 1 minus 0.05 or 0.95, for n minus 1, which is 19, 20 minus 1 degrees of freedom. Our chi-squared table should be appendix table 4, if I remember correctly, or table 6. So once you have that value from the chi-squared table, let me know what you found. $10.12. All right. We have value 10.12. I'm gonna write it to 3 decimal points, so 10.117. And now by just solving mathematically, we get that our variance has to be less than or equal to 0.0287. Of course, by definition, that tells me that my standard deviation will have to be less than or equal to 0.17. The units of variance were ounces squared, so my standard deviation will be 0.17 ounces. What this tells me is that the dispersion that I can expect in my machine can be as big as 0.17 ounces. Now, whether or not that is problematic for my machine is up to you, the engineer, to determine. Are there any questions?
Why did you use 10.1 again?
So, because that's the value we found from the chi-squared table. So remember, just like we have the z-squared table and the t value table, we also have chi-squared table. So for 0.95 and 19 degrees of freedom and n minus 1, the value for the table gives you is 10.117.
I mean, I was with Renee. I got.
That's fine. The textbook rounds them. So
Oh,
that's
okay.
fine.
Sure. Oh, okay. Sure.
Yeah, you're not wrong. That's what I'm saying.
Figure's less correct.
All right.
Okay, Professor.
Okay, there are no
Professor.
questions. Oh, sorry. Go ahead.
Yeah, I have a question on the in-class problem.
Okay.
Yeah, you said we have to turn it in by 5 p.m. So my question, I just wanted to see how you for variance, that's how you did it. Then you drag the result just came up, but I've tried that, it didn't work for me.
So you got a different value for your variance, if I'm understanding correctly?
Yeah, you did the first value, which was 0.497052, then you had to drag it, then every other values came out in the box or in the boxes. So I wanted to see how you did that again. Then the second was the lower and the upper. The upper, I just wanted to write down that formula really quick because I see that we don't even have time to turn it in.
Yeah, so I actually closed my spreadsheet, but I think I know what the problem is. So if you're dragging everything, you need to make sure that your values are locked to the sample mean, which means that the sample mean cannot change. If you just selected the sample mean but didn't lock it, you lock it by pressing F4. If you didn't lock it, then that cell is going to move too. So if you got the first value correct, and you're getting all the other values incorrect, it's because you're not locking the sample mean. So once you select the sample mean, you press F4 and it'll lock it. That way when you drag, it's not going to move that value.
Okay. Then what about the formula for the lower and the upper?
So for that, I just selected the values directly from your cell for lower and for upper bounds. So there's no dragging required, right? I didn't drag anything there. I just typed in the equations almost manually, right? I just selected the values directly.
Okay.
And once again, if it doesn't work out in Excel, you can always calculate it on a calculator, right? Just to make sure that your numbers are correct.
Okay.